In this lesson, we're going to explore the EAS reactions of substituted benzenes, looking at how existing substituents can affect the regioselectivity of the reactions. The substituents on a benzene ring can have a big influence on the rate of an EAS reaction. Activating substituents are those that accelerate an EAS reaction relative to benzene. Deactivating substituents are those that slow an EAS reaction relative to benzene. Let's take a look at activating groups first. Activating groups accelerate EAS reactions by increasing the electron density in the benzene ring, making it more nucleophilic. Activating groups can increase the electron density in the benzene ring either inductively or through resonance. Inductive activators include alkyl groups and other hydrocarbon substituents. So here I show toluene as an example, having a methyl substituent. Inductive activators tend to have a very weak activating effect on benzene. They enhance the rate of the reaction by providing extra electron density to the benzene ring relative to a hydrogen. An alkyl group simply has more electrons in it than a hydrogen atom. Resonance activators will typically have an oxygen or a nitrogen atom that's not positively charged bonded directly to the benzene ring. Resonance activators vary from moderately to strongly activating. So here I show methoxybenzene or anisole as an example. The lone pair adjacent to the benzene ring extends the conjugation and can place extra electron density into the benzene ring through resonance, increasing its nucleophilicity. Deactivating groups decrease the electron density in the benzene ring, making it less nucleophilic. Deactivating substituents can remove electron density either through induction or through resonance. Inductive deactivators typically have an atom with a full or partial positive charge bonded directly to the benzene ring. Halogen substituents also can be considered inductive deactivators. So here I show the conjugate acid of aniline as an example. You can see that the nitrogen directly bonded to the benzene ring has a full positive formal charge. The impact of inductive deactivators largely depends on the extent of positive charge adjacent to the ring, and can range anywhere from weakly to strongly deactivating. Resonance deactivators remove electron density from the benzene ring through resonance. These typically have an atom with a pi bond to a more electronegative atom directly bonded to the benzene ring. So here as an example, I show nitrobenzene. You can see that in that nitro group, the nitrogen that is directly bonded to the benzene ring is also pi bonded to an electronegative oxygen. That pi bond is conjugated to the benzene ring, and electron density can be removed through resonance, decreasing the electron density in the ring, making it less nucleophilic. The substituents on a benzene ring can also impact the regioselectivity of an EAS reaction. An EAS reaction on a monosubstituted benzene can result in the formation of ortho, meta, and para products. Substituents can affect the regioselectivity of an EAS reaction by altering the relative electron densities at the ortho, meta, and para positions. Ortho-para directing substituents are those that tend to give ortho and para products largely to the exclusion of meta products. And it turns out that all activating substituents are ortho-para directors, as are the halogen substituents. Meta-directing substituents are those that tend to direct EAS reactions to give the meta product, largely to the exclusion of the ortho and para products. Conveniently, all deactivating substituents except halogens are meta-directors. In order to see why these trends in regioselectivity exist, we need to take a closer look at the reaction mechanism. So here I show an EAS reaction of toluene, which has an inductive activating group. The first step in an EAS reaction is the formation of the bond between the benzene and the electrophile, and results in a resonance-stabilized carbocation intermediate. So here I have drawn out all of the resonance structures that would be formed from ortho, meta, and para attack of an electrophile in the first step of an EAS reaction. In each case, 3 resonance structures exist, spreading out the positive charge over 3 carbon atoms. In the ortho reaction, 2 of the carbocation resonance structures are secondary carbocations, and the third is a tertiary carbocation. The same is true for the para attack. 2 of the resonance structures are secondary carbocations, and the third resonance structure is a tertiary carbocation. When we look at the meta attack, we can see that all 3 resonance structures are secondary carbocations, and we know that tertiary carbocations are more stable than secondary carbocations. The ortho and para attack each result in one resonance structure being a tertiary carbocation, making the overall structure more stable, reducing the transition state energy, and making the reaction faster for ortho and para attack. The explanation of the regioselectivity found in a resonance activator is a little bit different. So here I show the first part of an EAS mechanism starting with methoxybenzene, which has a resonance activator. In this case, we can see that both ortho and para attack results in the formation of a resonance system with 4 resonance structures, while the meta attack results in a resonance system with only 3 resonance structures. The extra resonance structure found in the ortho and para attacks spreads out the positive charge, stabilizing the intermediate and leading to a faster reaction. The story changes again when we look at deactivating substituents. So here I show the first mechanistic step of an EAS reaction starting with the conjugate acid of aniline, which has a powerful inductively deactivating substituent. We can see that regardless of the position of attack, a resonance system with 3 resonance structures is formed. However, if we take a closer look at the resonance structures formed from ortho and para attack, we can see that in each case, a resonance structure exists which places 2 positive charges directly adjacent to one another. Placing 2 positive charges adjacent to one another greatly destabilizes the intermediate. That makes the transition state leading to that intermediate less stable, raising the energy of activation and making the reaction slower at the ortho and para positions, allowing the meta attack to dominate. Substituents on a benzene ring can also affect the regioselectivity of an EAS reaction due to sterics. Specifically, large, bulky ortho-para-directors can inhibit an EAS reaction on the adjacent ortho carbons. So here I show 2 contrasting examples, each with a single ortho-para-directing alkyl group. In the first example, the steric bulk of that large group effectively blocks the ortho positions, forcing the reaction to occur mostly at the para position. In the lower example, the smaller methyl group has much less impact over the neighboring ortho positions, leading to a mixture of ortho and para products. So what happens in an EAS reaction when the benzene reactant has more than one substituent? Fundamentally, 2 groups on a benzene ring can have directing effects that either reinforce one another, favoring the same regioselectivity, or conflict with one another. This first example demonstrates reinforcing directing effects. Here, the benzene ring has 2 substituents, a methoxy group, which is a resonance activator and therefore directs ortho-para, and a carbonyl, which is a resonance deactivator and therefore directs meta. And because of their relative placement, the positions that are ortho and para to the green methoxy group are also the same positions that are meta to the red carbonyl. In this case, the 2 groups reinforce the same regioselectivity. Between the 2 preferred positions, the bromination would likely occur at the bottom carbon, simply to avoid steric strain with the larger methoxy group. The second example demonstrates what happens when the 2 substituents conflict with one another with respect to their directing effects. So here we have a disubstituted benzene with the same 2 groups we had before, except now they're positioned differently. Again, the green methoxy group will direct ortho-para, and the red carbonyl will direct meta. But in this case, the 2 groups are not directing to the same positions. In cases where 2 groups have conflicting directing effects, the stronger activating group typically dominates the regioselectivity. In this case, the methoxy group is a powerful activating group, and the carbonyl is a powerful deactivating group, so clearly the methoxy group is the more powerful activator, and will dominate the directing effect. Placement of the bromine between the 2 larger groups is less likely due to steric strain, and that means that reaction will occur at the 2 remaining sites, leading to a mixture of products shown here. Now that we understand how substituents on a benzene ring can affect the regioselectivity of an EAS reaction, we can start to explore how multiple reactions can be sequenced to affect a desired overall transformation. So here I have a couple of examples. The first one relies only on EAS reactions. The goal here is to transform benzene into 1-bromo-3-nitrobenzene using a sequence of reactions. We know that the 2 substituents, bromine and nitro, can both be introduced using only EAS reactions, the EAS halogenation and nitration respectively. And that means it's going to take at least 2 reactions to achieve this transformation. But the order of those 2 reactions is critical. We can see that the 2 substituents are positioned meta to one another. And that means whichever group we place onto the benzene ring first needs to direct the second reaction in a meta direction. The bromine substituent is a halogen and therefore directs ortho-para, but the nitro group is a resonance deactivator, and that means it directs meta. So we can conclude that the nitro group has to be placed on first, using standard EAS nitration conditions. The nitro group will now direct the halogenation using bromine and iron bromide to the meta position because a nitro group is a meta director. The second example relies on a mix of both EAS and other types of reactions. In this case, the goal is to transform benzene into 1-chloro-3-ethylbenzene. Both the chlorine group and the ethyl group can actually be introduced directly through EAS reactions. The chlorine through halogenation and the ethyl group through Friedel-Crafts alkylation. The two groups are positioned meta to one another, and that means we need to introduce a meta-directing group first, forcing the next reaction to occur at the meta position. And therein lies the problem, because both the halogen and the alkyl group are ortho-para-directors, and no matter which of those two groups we placed on the ring first, the other group would be forced to go ortho or para to that group, not meta. What this tells us is that one of those two groups at one point in time had to be a meta director. So what if instead of placing an ethyl group on through Friedel-Crafts alkylation, we introduced a 2-carbon carbonyl group through Friedel-Crafts acylation? A Friedel-Crafts acylation using a 2-carbon acyl chloride would introduce a 2-carbon chain as a carbonyl. A carbonyl group attached directly to a benzene ring is a resonance deactivator and therefore will direct meta. We can then perform a standard EAS halogenation using chlorine and iron chloride to place a chlorine meta to the carbonyl. We can then transform that ketone into an alkyl group using a deoxygenation reaction, specifically a Wolff-Kishner reduction. So you can see that in this example, we needed to transform one of the groups that was introduced through EAS chemistry using a non-EAS reaction, specifically a reduction. These two examples represent, at a very fundamental level, the planning and strategy involved in making very complex organic molecules, useful molecules like pharmaceuticals,